cable, hardware, and splitters relate to each other. The topology is the physical layout view of the network, where components are actually located, how they are connected, and how the architecture is actually implemented on the map. The topology may look the same as the architecture or very different, even though it provides the logical function dictated by the architecture. Service providers deploying FTTX networks using point-to-multipoint PON topologies have a fundamental architectural choice to make regarding splitter placement in the network. This involves using centralized, single-stage, or cascaded, multi-stage splitter configurations in the distribution portion of the network. Both are deployed for a number of reasons according to the desired outcome of the business plan, and both come with their own set of advantages and disadvantages. We will look at the central switch home run architectural model first. With this way to deploy FTTH services, a 1:32 splitter is located inside the central office CO with a single fiber directly routed from the splitter to each subscriber. From a pure efficiency standpoint, this is the best way to deploy FTTH services, with each subscriber having a dedicated fiber from the central office or head end, as that gives the service provider a lot of flexibility in what and how services are deployed. Also, there are no network interface points between the CO and the subscriber, so all maintenance is done within the central office, reducing operational expenses. The downside of this design, though, is the number of fibers that would be required in the OSP cables and the central office. Allowing for spare fibers and future growth would result in there having to be significantly more fibers in the network than subscribers. This strategy is only really effective, though, where service areas are very close to the central office. The local convergence architectural model is slightly different. This architecture centers on the FDH, or Fiber Distribution Hub, where every end user or building in the neighborhood is represented. It makes very efficient use of the splitters, maximizes accessibility, provides easier troubleshooting, and accelerates turn-ups and reconfigurations. The architecture typically begins with a 1:32 splitter placed inside the FDH, with the 32 split fibers routed through distribution panels, splice ports, and/or access point connectors to the ONU at 32 homes. A series of terminals make up the distribution side of the FDH. These terminals may be integrated into the network using splices, connectors, or a combination of both. While splice terminals offer great flexibility in how a network can be installed and the lowest optical loss, they require much higher labor costs and additional time for deployment. Almost every network will employ some combination of splices and connectors where they make the most sense. For connectorized options, hardened connectors add some significant benefits. These are specifically designed for use in harsh environmental conditions and will speed up deployments while reducing labor and installation costs. Both the FDH and terminal tails can be connectorized with hardened multi-fiber optical connectors, or HMFOCs, for easily connecting 12-fiber OSP cables in the distribution network, allowing them to just plug together, providing a more fully connectorized architecture. A fully connectorized, centralized approach using an FDH offers some attractive benefits: speed of deployment, maximum long-term flexibility, and future-proofing aspects. Maximizing the use of connectors instead of splices whenever it makes sense enhances the accessibility of the network. One ideal area for a centralized approach is where take rates are not guaranteed, but may increase steadily as the area is further developed over time. Centralized splitter architecture advantages include OLT utilization, pay as you grow. A centralized splitter architecture allows the operator to concentrate active customers on a few OLT ports. For example, 200 houses representing 200 potential customers are concentrated or brought together at a centralized splitter point. From this, a 1:32 splitter will serve the first 32 active customers in this cluster of 200 houses. As we'll see, the focus in decentralized splitter architecture is different. There are trade-offs in both architectures between the take rate and the utilization rate. It is future-proof and easy-to-change technology, as the nature of single-stage connectorized splitting allows providers to easily adapt to changing subscription patterns, split ratios, speeds, and new technologies. For monitoring and maintenance, this topology can reduce operational expense, OPEX, through convenient and easy technician access for maintenance and reconfigurations in a single location. Fewer truck rolls are required. Record keeping is simpler, as are upgrades to the technology and additions of new customers. Centralized splitter architecture disadvantages include that this approach generally requires deployment of more fiber in the outside plant, particularly in the ODN or optical distribution network. This can result, without even taking into account costs for civil works, an incremental increase in capital expense, CapEx, of over 38% compared to a cascaded topology. Larger network elements in the OSP, optical splitters with high split ratios, require more fiber and must be terminated to the customer either through individual splices or connectors. The splitters and termination fields are generally housed in street cabinets, which are more expensive than closures and occupy more real estate. They are also subject to more stringent regulations from local or government planning bodies. All this can add time and cost to the deployment. In the centralized architecture using closures, the feeder cable from the central office is connected to a closure instead of an FDH at the fiber distribution point of the network. The closure performs as the splitter housing. However, while an FDH leverages connectorization as much as possible, the closure system is typically spliced together. Still, the closure remains accessible for adding splitters at a later time, so it's possible to deploy the network for an expected take rate and add splitters if the take rate increases. Additional closures can be deployed downstream from the main closure to further extend the network. The architecture begins with the feeder cable running from the central office to the closure, where it is spliced to the splitters inside. The splitter outputs then extend out to a few splice closures. This architecture is designed for very small distribution areas, so there are typically only a few splice closures and a relatively small splitter count. The distribution fibers are spliced into drop cable splice closures, such as the hybrid connector splice closures, and drop cables are spliced in for connecting the ONUs at each home. Since the centralized with closures architecture is typically spliced together, equipment costs are minimized, but lower initial costs may be offset as time goes by reduced flexibility and higher maintenance costs. This type of architecture is ideally suited to very small distribution areas, such as one requiring only 2 splice closures off the main closure. Another option is to look at the distributed split architectural model, where the splitters are placed deeper into the network. In most cases, a cascaded or distributed splitter approach has no splitters in the central office, as the OLT port is connected or spliced directly to an outside plant fiber. A first level of splitting, 1 to 4 or 1 to 8, is installed in a closure not far from the central office. The input of this first level splitter is connected with the OLT fiber coming from the central office. A second level of splitters, 1 to 16 or 1 to 8, resides in terminal boxes very close to the customer premises, each splitter covering 8 to 16 homes. The inputs of these splitters are the fibers coming from the outputs of the first-level splitters described above. Cascaded splitter architecture advantages include lower CapEx. Differences in CapEx between cascaded and centralized topologies greatly depends on the demography and density of the area. In a cascaded topology, the amount of fiber required is much lower in the network's distribution portion, the area of the network with the greatest impact on the overall cost of the infrastructure. If civil works are necessary in the distribution area, the greater amount of cable in a centralized topology means more ducts, and obviously more expensive digging. CapEx differences also depend on the individual operator's business case and expectation of successful initial take rate, so the costs for all contingencies must be weighed during the planning phase, as a thorough costing exercise of possible expenses is requisite. Other advantages include where all the drops are made at once in a single place. In a cascaded topology, when connecting a new customer, the drop is installed from a terminal box close to the premises, usually at a distance of tens of meters, allowing all the work to complete the service turn-up to be done inside the premises. In a centralized topology, in addition to this step, the technician must also go to the cabinet or closure containing the splitter and make the appropriate connection there. This extra step can be easy if good records for the cabinet are kept and appropriate cabinets are used. Unfortunately, this is not always the case, and inaccurate or incomplete circuit identification, as well as improper fiber handling in the cabling or confusion during splicing, can create delays and cost money. Cascaded splitter architecture disadvantages include that there are more actives and more splitters. Unlike the centralized topology, in the cascaded topology, the operator focuses on assuring that the last splitter in the cascade serves the largest number of houses or customers. If, as is usually the case, initial take rates are low, overall utilization rate of the central office will also be low, and there is a risk of stranding OLT port capacity. This method also makes it a less flexible network. 2 splitter steps are most common in cascaded topologies, especially in new builds, although at times 3 steps are required, resulting in a rigid network. In as short a period of time as 4 to 6 years, new technologies, new services, and ever higher speeds drive network upgrades. Introducing changes, therefore, in a rigid cascaded network can be difficult, time-consuming, and costly. In the distribution network, splitters with new split ratios may be required, and if this is done within central offices, thousands of patch cords must be unpatched and patched to remove existing splitters or to install new ones. Another disadvantage is monitoring and maintenance. Splitters in a cascaded topology are often spliced rather than connectorized. Test equipment such as OTDRs are blind after splitters unless reflectors and sophisticated monitoring systems are used, as they will not recognize failures. In a cascaded topology, monitoring always occurs upwards from customer to central office, so typically in a centralized topology, all monitoring can be done from the cabinet where the splitters are located, both downwards to the customer premises and upwards to the central office. In a cascaded architecture using splice closures from the central office, the feeder fiber enters the closure and passes through the first splitter. The output fibers then feed into smaller closures or fiber access terminals that are closer to the customer. At each smaller closure, a distribution fiber enters another splitter. The drop cables from each customer premise are then connected to the outputs of these splitters to complete the network connections. The cascaded with closures architecture is typically spliced from the hub closure to the splitter inputs at the fiber access terminals. The feeder fibers are spliced to the splitter inputs, and the distribution fibers are spliced to the splitter outputs. In the fiber access terminals, the distribution fibers are spliced into the splitter inputs. There are pre-connected adapters on the splitter outputs to allow fast connections with pre-connectorized drop cables. This half-spliced, half-connectorized installation accounts for the majority of today's cascaded networks. In areas where high take rates are projected or in extremely rural areas where fiber costs become more significant, connectorization at the customer side can be a great fit. This architecture is extremely fiber efficient and is based on a cascaded approach. To illustrate this architecture, let's take a 1:32 split ratio and a single 12-fiber cable placed throughout the service area. This single cable is used as both the feeder fibers and the distribution fibers. Fibers 1 to 8 are the feeder fibers, and each will connect from the central office directly to a stage 1 splitter somewhere in the service area. Fibers 9 to 12 are the distribution fibers that connect a stage 1 splitter to a stage 2 splitter. These distribution fibers are divided into segments along the length of the cable, with each segment serving only the local area. Since the distribution fibers 9 to 12 do not directly connect back to the central office, they are reused throughout in each local area. The figure illustrates this fiber reuse architecture. Fibers 9 to 12 in the cable are reused 8 times because there are 8 segments, one segment for each feeder fiber from 1 to 8. Thus, a single 12-fiber cable can service up to 256 homes by combining feeder and distribution functions. The fiber reuse model is particularly effective in a large rural or MDU setting because all the components, including the fiber itself, are relatively small. The terminals or closures are also quite small, having minimal aesthetic impact to the neighborhood or building. It should be noted that the fiber reuse architecture can be significantly more difficult to design, engineer, document, and service. However, it is extremely efficient in terms of fiber usage, and the equipment costs are lower. This architecture should clearly be considered in large rural areas or for MDU applications where smaller equipment size, ease of installation, and overall aesthetics are important requirements. Fiber indexing uses a fully connectorized system and allows installers to use a cookie-cutter approach to build out the network. The exact same components are daisy-chained together, limiting the need for custom cable assemblies or splicing. The basic building block, which is repeated throughout the service area, includes a connectorized terminal with a connectorized tail and connectorized single and multi-fiber outputs. The indexing begins with a 12-fiber cable entering the first terminal. In the terminal, fiber 1 is routed to a splitter for servicing local customers, and the remaining fibers are indexed or moved up as they exit the terminal to connect to the next terminal. Indexing means that the second fiber entering the terminal will exit as the first fiber to enter the next terminal, and so on in a daisy-chained fashion. There are several variations of this architecture so it can meet the requirements of many deployment scenarios. By using the same components over and over throughout the network, along with less overall fiber, the network can be installed faster and with lower overall installation costs. Fiber indexing offers several attractive benefits to service providers choosing a distributed architecture for their access network. Using the same terminal, same splitters, same fiber cable, and adding cable spooling technology makes a good case for fiber indexing in many access applications. The addition of connectorization, whenever it makes sense, reduces the need for more highly skilled labor, further decreasing overall costs. Let's watch how this process works.